I'm going to talk about software, and so this is a software talk, so I'll try to make it quick. I know we have to introduce the software. Nobody likes to hear too much about software, but it's everywhere, and you need it to do data analysis nowadays. So I'm just going to go through the general interface that we have for mitochondria. This is mainly the mitochondrial analysis software. The STR analysis software is very similar. Features, a little bit about how the data processing is done, and some details about how the data analysis is done. So what we have is in-house for all of our assays, we have a database that keeps track of assay plates and samples. There's a catalog of reagents and samples that go onto plates. For Steve had earlier described some of the IBIS technology and how it's used for identifying bacteria and viruses, fungi, parasites. The same basic database is used for all these things, including what we're doing here with mitochondrial or STR analysis. We have a 96 well plate and we put samples on it. They get tracked in a database, and there's primer pairs in those reactions, and the primer pairs basically define for software what to do with it. So you register an assay, you register a template and samples, you tell the database you're running an assay, then you actually run it, then it goes through mass spectrometry, and there's some data processing that goes back to the database then, and then the analysis software takes what you put into your plates and the data that came out the back end, puts it together and gives you a display that you can then look at and verify and interpret. And then there's some options for, well, in this case, for this assay, profiles. You can do pairwise or comparisons or search a database. One of the things John pointed out for STRs, for example, it's backwards compatible with existing databases. Our mitochondrial assay is also backwards compatible with sequences, because you can take any sequence, if you know the primer pairs you're using to amplify it, you can calculate the base composition that would result from our assay. What that means is you can compare a result done with the mitochondrial assay to the population database developed at the FBI, for instance. You could also develop a database using this technology, and you could sequence a sample, and you could compare that to a database that you've created with base compositions. Because you can take the sequence, you can convert it to base compositions and do a search. And then if you think about what Les had said, where the mitochondria is just one big molecule, what that means is you can't take polymorphisms and treat them independently and multiply them together to get an expected frequency. If you know the frequencies of each SNP, it doesn't make any sense. They're all one unit. Because of that, you have to use the counting method basically to look empirically from a population that's been analyzed already. How many times does this profile occur? You can do the exact same thing with base compositions. So you can treat them statistically the same way as you treat sequence profiles if you're doing a database search. So you can get expected frequency in any population, provided you have data. You can calculate the upper bound that you'd expect, a 95% confidence interval. It's all basically the same thing. And then some reports can come out the other end, stuff. So the software we use leverages what we already had in place for our other assays. That's a tracking database to keep track of samples and such. And then we have a module that we plug into it, and updates can be made independently then. We can update our software, add features, and just plug it into our existing software. It provides utilities and functions to basically look at the output of a reaction or a sample or set of samples, verify everything looks okay, and interpret it. It also gives you utilities to help basic keeping track of a database, searching and comparing profiles. So here's one step that goes in between the data processing that's automated here from after you register and run an assay. It goes into a thermocycler once you've set it up, and then you'll see this later on and when you run samples, you'll see this happen. Once it's gone through thermocycling, it goes on a machine and everything else happens automatically up to the point where you get presented with results. This part, the controller for the instrument triggers data processing after a plate is run. That goes through processing and imports the results back into the same database. So then when you go to analyze something, it's just there on the screen for you. This is, I'm not going to go into a lot of detail here. There's a monitor that you can look at and you can re-trigger plates if something went wrong. There's a step, we're very fortunate at IBIS because we, part of our, what we do for analysis, this came from a collaboration with the SAIC in the past with a DARPA contract to develop a novel biosensor for detecting biowarfare agents. Steve had talked about it earlier. And the people who wrote the signal processing that would look in raw mass spectra for signals and correlate them to base compositions and organisms, things. Or at the SAIC, there were signal processing experts, and they did radar, signal processing and such. Well, we were very lucky that a genius in this kind of thing came to work for us, and he created this algorithm that would take this and turn it into that without any, you don't have to interrogate signals, you don't have to ask for hypotheses. It just turns this into that, and all the signals taken into account, and it's very straightforward. It's simple, but it's ingenious the way he does it. And we run that automatically, and we spit these out one after the other. And we then can derive numerical masses right off of the spectrum. We can put that back into a database and makes analysis very simple and straightforward. Then after the data processing, we go into the analysis module. And this is what the interface looks like. So when we come in tomorrow, there's going to be only 4 of them, but there's going to be computers on the tables. And then you'll get a chance to look at the software and try it out. This is the basic interface for currently for the T5000. That'll change in the future. Here's context menus over here. So this is for mitochondrial analysis. You'll see one there's down here for STR analysis. We're not going to go through that right now. You'd click one of these options and something else will come up. So here's an interface that allows you to choose a plate. They're bar-coded, so they just have a code. I don't know if you can really see it. There's some timestamps. Everything's tracked by time. You'd select a plate, and then you get a layout from it. You can't really see it very well here. You can select a sample or do all samples. Click through there, and you press Analyze, and results hopefully come up. And here you saw Les had some of these in his talk. This is what we call a coverage map, an arbitrary term, but it's a map of products against the Cambridge reference sequence. There's some information about product assignments here. Each one of these products is 2 strands, so both strands are shown separately. There's a little number inside the green bar. That number is the parts per million measurement uncertainty based on the idea that you've got the right product assignment. The mass measurement is never exact. So this gives you an indication of how close you are. If it's really high, it gives you an indication, well, maybe you should look at that. There's always a level of uncertainty in any measurement. And then there's some details you can get. If you click on one of these, for instance, you get details about the assignment over here. Or if you mouse over it, you'll get details next to the mouse. And then there's a composition profile over here. Some details about a mass assignment if you click on one of these, or if you click on a peak. It's all kind of integrated together. These are schematic. They're like histograms. They're line plots of where a mass was called and what its approximate abundance was. There's a navigation interface, and then there's some utilities and such here. And then apparently more stuff. Forgot. So there's some utilities that I'm not going to spend a lot of time on. You can import sequences, and they'll be converted to base compositions because it's very straightforward for a computer to do that. There's a couple different ways you can do that. Some stuff for ranging samples. You can import mass files if something went wrong and the process was broken. This is an example of a single sequence addition. You could do this from a CMF file, for instance, or from AFTL has a system called Lisa. You can export from that and import here. Or you can type a profile in, or you can import a raw sequence in and align it and designate the profile itself. And then these also get stored in standard format in the database. So you can have sequence profiles, and then you can convert those to base compositions, or you can just measure base compositions. This is an example of a sample analysis again. You select the sample. I've been through this here. That's the top strand, the bottom strand. So that's the double-stranded assignment there for one product. The number in between in the bars is parts per million. Steve explained that. Basically, 1 part per million is whatever you're talking about divided by a million. So the parts per million measurement error or uncertainty is theory minus observed divided by theory times a million. Okay, so there's one strand there. It's integrated there. If you mouse over that, you'll see the peak that it corresponds to highlighted over here with a little red box. So you can kind of get your bearings. It's going to look a little, if you use the software, it's going to look a little strange at first, and then it kind of gets easy because you could look here and it'll tell you what well you're dealing with under the mouse. So you can scroll over here, or you can just look here and see what strand is highlighted there, and you can figure out where you're at. So there's a pair of products right there. It shows up in the profile there. That's the primer pair number. That's an IBIS database thing. These are the CRS coordinates, and this is the base composition for that piece. So one reaction then will have 3. You can see they're kind of spread through the profile because they're separated, so they'll amplify together. Now we also, Steve had talked about the coins and the scale, and he pointed out that we use a mass tag, a special nucleotide, and he already went through this, so I'm going to go through this briefly, but I'll show you what it means in terms of our assay in a second. So if we have this base composition, for example, if we had a SNP, it's no problem. A T to C SNP will move over to about here. That's about 15 Daltons. And on the other side, it'll move over there. If we had an A to G, it's also going to do almost the same thing. But if we have them together, then it moves almost back. So what you'll see here is a G to A or an A to G, depending on which way you're going. So if it's an A to G and a T to C, the 2 strands, the forward strands of those 2 products are only 1 Dalton away from each other. That's a hydrogen atom. And the 2 reverse strands are only 1 Dalton separate. So that makes it, with our normal precision, said we get about 10 parts per million. That's about 30 for a 120 base pair product. So we say, well, that's fine. We can resolve that. Well, first, well, number 1, you couldn't resolve them if they were in there together. They'd be 1 peak. Number 2, and I'll show it in a second, we get an average precision or accuracy of 10 parts per million, not 10 parts per million every single measurement. And the trick is to know when you're off. So rather than dealing with that and trying to do something we can't really do very well, making exact measurements where we know we never have to worry about being off by more than 10 ppm, we change the rules of the math. So we use a nucleotide. The beauty of using a stable isotope derivative, we use carbon-13 enriched guanosine. It doesn't change the chemistry. So the chemistry is all the same, it's just heavier. So we don't have to worry about incorporation in the PCR. It all works the same way. What it does, though, is it moves up the mass for every G that's incorporated into your product. The mass is about 10 Daltons heavier. Now, every time you have a G, though, it's paired to a C, so you don't get the same mass shift on the other side. So it separates the products from each other when you have SNPs. Is this making sense? So you'll see those same 2 products that I showed back here should be here, and this is simulated data here. Now that's still simulated data, but that's real data. So this this is what it should look like, and this is what it does look like. Now the difference here, just to be clear, this is the position in gray of where it would be if it wasn't tagged for this particular set of products, and this is where it would be if it was tagged. In this case, this is where a set of products really were, and these that are gray just happen to be other products in the reaction because this was a multiplex reaction. So this set of gray and this set of gray aren't the same, but the colored ones are. Does that make sense? Okay. And these were just two different samples we've been dealing with. Now, what does that mean in general? If you look at one particular case, you can say, okay, that's great. We can tell them apart, we can separate them. Here now, if you look at any base composition, if it's 35, 40, 23, 18, for instance, we always go A, G, C, T. That's just our standard nomenclature. You could blank it out and call that 0, 0, 0, 0. And anything you're comparing it to then is +1, -1, or else 0, 0, 0, 0, which would be the same. +1, -1 is an A up and a G down. So you can take anything and compare any other product to it if you're dealing with just the masses in terms of base differences. And what would the mass differences be at that point? So if we have anything starting at A0, 0, 0, G0, C0, T0, and we go up 10 A's or down 10 A's, up 1, 2, 3, 4, 5, or any of them, combined with G up or down 10, or any combination thereof, and C and T as well. So all combinations of up and down 10. And we say, with that in mind, up and down 10, for increasing product length and increasing measurement error, starting at short with no error up to long with high error, what we see is, just mathematically, what you'd see is for product length increasing from 0 up, well, 0 doesn't make any sense, but up to 200 on this plot, with mass measurement error of exactly spot on, no error whatsoever, up to 100 parts per million. Within our normal working range, now we say we get an average of 10 parts per million. Our normal working range is less than 20 parts per million when you consider standard deviation, but that's not all the measurements. 94% of those, I don't know if you can see that clearly, but this little overlay just skirts the boundary of where you start to see multiple possibilities when you consider how long a product you're looking at and how big an error you have in your measurements. So this is the potential ambiguities for any base count. In this flat area, there aren't any. You get one answer. But as you go up in length, just like if you put more coins on a scale, eventually you're going to get a combination that you can't tell which coins they are. There could be more than one combination, which is true for base compositions too. But for us, it's sort of like you had 2 bags of coins, and one bag of coins dictates what the other one must be. So you get a little more that way. But still, even with double-stranded, these ambiguities take that into account. So if you're at 175 base pairs with a 60 parts per million error, you get more than one potential answer. Okay, so 94% of our measurements over a set that we just took out kind of randomly of 123,000 measurements that have been made, 94% of them were just fine. You couldn't make an error. 6% of them were outside that working range, however. Now that's not so bad. I mean, 94% is a pretty good number. The question though is, if you don't know already ahead of time that those, which 6% you have, which 6% are the problem. Each measurement it looks just fine when you look at a peak, right? So where are the problems? Which 6% do you have to deal with? Well, that makes everything suspect. So we change the rules there, and we use a tag, right? And then that, using the mass tag and the up and down 10, A's, G's, C's, and T's, and all combinations thereof, changes our working range. Okay, now if you go farther, you can start getting ambiguities again, say 20 A's and G's and C's and T's. There's a lot of possibilities. But we're dealing with a somewhat constrained system. With STRs, we're dealing with a very constrained system. With mitochondria, we're dealing with a constrained but not as constrained. Each product is a limited length. There aren't unlimited mutational possibilities for switching bases around. So that puts all of them in this working range at that. But it also tells us where we can assign our error tolerances. So for the biggest product, as I said in the talk earlier, it's about 150 is about the biggest thing we've seen. And that's in one particular region of HV2. And the intersection of where ambiguities start to happen for that length, you'd see that starts in right after 80 parts per million. And then we set that back about 7 to 70. That way we can cast a wide net without having to worry, so we don't have to worry about missing things, but we also don't have to worry about making the wrong call. So we have a basis for saying, you know, setting that. Is that clear? Does that make sense? Okay. Now, to help with the analysis, you can then also look at the data, which can be very useful at times, especially if you see a mixture. So there's a spectral viewer. The easiest way to get to it is you just click on this little button here for any given spectrum, and it'll pop up the data, and then you can look, you can zoom, and you see the peak. For any product that's assigned, you'll see an overlay is automatically put there. That's just a Gaussian distribution. It's nothing fancy, but it'll scale it to the data. And you can interrogate hypotheses with this too. So here's an example of a SNP heteroplasmy. And this is shown on the assumption that for some reason the software didn't call it automatically, but you can see it's there. So you can look at that, and then you can browse hypotheses from the spectral viewer. It's integrated to our database though, so it already knows what primer pairs went into that reaction. So if you click this button back here and you open up a spectrum, it loads that and overlays the products that have been assigned, but it also knows which primer pairs were there. And for those primer pairs, it knows, I went kind of quick there. First of all, it'll tell you what you've got on the screen. And then it also knows what products have been seen before, what's in the database for that primer pair, and you can browse through those. And you can just scroll through them with the arrow. You can choose specific ones, or you can move the bases around here. And as you do that, if all this stuff is set, you'll see little black overlays flip around on the screen until they lock on to what's actually there, and they'll line right up. And then you could go in and you can actually assign those very simply, and I'll show you how to do that. And then you can check for various things, like you might have I didn't go into any detail on this, but our reactions, they're all designed such that, in contrast to the way a STR, and I was talking to you about this, how STR reactions are normally done. You use quite a bit of magnesium, and then TAC polymerase likes to add an A to the end of a product. So with a normal STR reaction, it's going to be forced to try to have all the products have that extra A on them so they're all uniform and you can tell their length. And every so often you see this little minus A thing, right, you have to deal with. For most of our assays, we go the opposite. We try to make blunt-ended, clean products. And you can do that by lowering the magnesium, which actually helps in your specificity of the PCR as well. Get fewer cross products. And if you put a T on the 5' end of your primers, the product already ends in an A, and TAC is much less efficient in adding an A to an existing A, so you can blunt the products. But then you see the opposite artifacts where you see a plus A once in a while, and you can check for that to make sure that a product you see in a well isn't a mixture, it's just that plus A artifact you might see. Okay, so there's various things you can do if you're in the analysis interface. You can right-click and get a context menu. One thing you might do with that then is say, you might be running a sample, you had a problem with one, or you're just repeating a certain number of samples. So you might compare a sample to something that you've already registered in the database. If you've registered a sample in the database and it has a name, and you're running it again, and you do this, it'll automatically find it and pull it up, and you can do a comparison. And this is just a side-by-side comparison. It says these are the primer pairs, These are the products you're seeing. This is what was pulled out of the database. They're either the same or they're different. It's a quick QC check. If it was different, you'd see a number of pieces that are different. You can tell it's not the same. Or you could search the database. In that case, you get a choice of target databases. You could expand those and see the populations, if it's a population database. Some parameters you can choose. So this is a sequence database supplied by AFDL, which is very similar to the one which we also have from the FBI here, but I don't have it expanded. So there's 21 populations in this particular set. These are all converted to base compositions in our database, so a profile can be compared to all the profiles there. And then it'll do it, you can choose to constrain it to a set of primer pairs and get a matrix comparison, or to all existing available data, if that makes sense. Because they don't always start and end in the same place for a sequence. We can only predict a base composition if the full range of coordinates for a primer pair from the 3' ends where it starts amplifying, if those are represented in the sequence data. Then we can calculate the base composition, otherwise there's uncertainty. So what you'll get is and I'll explain this in a minute, a minimum number of differences between the query and the target and then you can check, the average or the standard deviation for a population. We can't measure the sequence when we measure a base composition. We don't get the order. And we could have compensating mutations within amplicons that blank out SNPs. So you could have 0 differences where you would have had 2 if you sequenced it. But likewise, you could have a difference here, or you could say there's 2 differences between these 2 amplicons. We can't prove that's not 4, and 2 of them compensated. So we say we can know there's at least 2, so we always refer to it as a minimum. There's at least 2 differences, or 4, or whatever it is. Now, comparing profiles is very straightforward, and as John had pointed out, with both of our assays so far, they're backwards compatible with databases. So what I'm showing you here is a comparison of 2 sequence profiles converted to base compositions, which is exactly the same as if they were both measured or one was a sequence and one was a measurement. Here, first thing between these two is and I'm using sequences just because then I can show you also, you can just compare over the data that are in common between 2 profiles. So this won't be a comparison of 2 full profiles because there's no data here. So it's grayed out because the sequence coordinates didn't cover that space. So we just go right down the list, say, okay, there's one minimum difference between these two. See, there's a C to a T. There has to be at least one. Those 2 are the same. That one has at least 2. That one has at least 2. That one has 1. This has an N in this sequence. There's no N registered in that sequence, but we don't know what that means, so these could be the same, so we say they're not different. That has 3 differences in those, and then the rest of them are the same. So you could just add these up, except you can't really because our primer pairs overlap, so you have to account for that. And that amplified coordinates, you have to take into account the number of coordinates that overlap and what the SNPs were, and if there's an A to G and 2 primer pairs that overlap, well, they could be the same, they probably are. So this whole region has at least 2 when you take them into account together. There's 3 there. They obviously can't be in common here, they don't overlap. There's at least 6 between these 2. And actually, if you do a matrix comparison of a set of samples, say Caucasian, it's not that far off from sequencing. Like I think Les had said about 8 differences between most people. I think we see like 7. I can't remember the exact number. It's pretty similar. So then you can take these when you've developed a set of profiles from a plate, 1 or more. You can just click this. If they're all okay, you can click the register and they just go into the database automatically, so you don't have to do anything extra. It's integrated. Then you can generate a report. It goes, you can put some comments here, and then this is for a plate, and you could click through the samples and put sample-specific comments here if you wanted to. Down here is a dynamic comparison between samples on a plate, just in case you're worried about contamination. And make sure that sample 1 isn't exactly the same as sample 6, for instance. If it is, you might want to look at why, or the negative for that matter. And then you can click that button and it'll generate a report. There's a couple different, very minorly different report formats. And that's just based on words, things like pass, fail. If you're a forensics investigator, you might not like the words pass and fail for different things. We use it for databasing in terms of, does this sample pass what we consider a requirement for putting it into our database? Or if you're doing a case, you might say it's a full profile or a partial profile, not that it failed, because there's a difference there. This is just a set of NIST samples that were run. You get some just details. What were the samples? What were their names? How much DNA was registered in the plate? This may say DF for an unquantified sample. It'd be a dilution factor. This is just an acronym for our negative control. It doesn't mean anything. It's a dilution buffer. Our positive control. And there's a way to register things as negatives and positives. So it'll verify the positive control profile if it's registered as a positive, and it'll fail it if it's not the expected profile and only the expected profile. Then it's not a passed positive control. And then a little summary of things that have been registered. The parameters that were used that are stored in the database will be listed, so they're tracked, and they'll tell who was logged in, what time it was generated, and some details if you ever had to go back and look at the plate to see did something go wrong. Well, this was the barcode of the plate that the PCR reactions were done on. That goes through the instrument, and the instrument automatically registers the rest, which is a magnetic bead cleanup plate and what we call an ESI, electrospray ionization. It's the final plate as a barcode starts with a P. It's tracked there so you can look at it later. This is a summary you get on each sample. You get one summary page, and it's kind of a schematic rundown. It shows what the profile was in comparison to the other profiles on the plate, and some details. Spectral views of the negatives come out on the report, so you can verify if you want to verify the primers were put in. It'll look for the expected positions in the raw data, not the deconvolved data, for one charge state of each primer. And then something you never want to look at, it's a log, just so that everything is tracked. There's a very gory detailed log of every assignment that was made, top and bottom strand, the error, the base composition, expected mass, observed mass, and this big list, and it just goes at the end of the report. And then when you generate a report, it shows it to you on the screen, but in the back end, behind the scenes, that report actually goes into the database. And if you're not logged in as the administrator of that schema, you can't delete it. So if you generate another one, somebody else could go retrieve the first one. Therefore, if, for instance, if a report was generated, the negative had failed, and then a report was generated and all the products from the negative were filtered out and looked great, the original report's in the database. So that's basically most of the mitochondrial software. The STR software is similar. It's not finished. Well, nothing's ever finished, but this is a little more finished. So everything, the main thing to remember, everything after putting it onto the, after thermocycling is automated. And then there's a manual interpretation step that you do with the software. And with that, questions? Yes.
Why did you choose to go the -A route? I mean, I understand you'll get better specificity from lower magnesium, but you also presumably decrease your yield potentially.
Two reasons. One that wouldn't seem obvious to everybody is it's just easier to fit in with manufacturing when our company does so many other assays that work that way. I can use exact same buffer to develop the reactions. It goes into manufacturing under the same buffer conditions. They don't need to deal with extra details. And it's a little bit cleaner. Yeah, so in fact, all the data that John showed for the STRs. To make multiplexing of the STRs easier, it was generated with a plus A modality with a stronger buffer. More magnesium and a bunch of betaine that helps kind of buffer out differences in amplification. I'm going back, actually, and trying to clean up the reactions by using our other strategy of taking the A's off. Turns out not every single time TAC adds an A, just like anything else in biology or biochemistry. Doesn't seem to be always an A. Sometimes a G gets added. Every so often a C might get added and a T, so it gets a little noisier. You don't see that in a CE because you get the length.
And how low is the magnesium? How low would it go?
1.5 millimolar total. And if we bump that up to 3, you get more adenylation. Yes?
So, at the end of this, do you get a mitochondrial profile, or do you, like, we're used to looking at a list of bases, but do I get a profile overall of, like, this entire mitochondrial, over this region there's, 75 or 750 Cs, or do we keep looking at it under the primer pairs? Does that make any sense?
Yes, it made sense. We get a profile, but the way we define the profile is 24 individual segments.
So it always stays separated by primer pair?
It's always separated by primer pair, and it's almost exactly the same as a sequence, if you think about it a certain way. Our sequences each position of our sequence has more than 4 possibilities, and each position doesn't have the same number of possibilities. Otherwise, it can be treated the same as a sequence, except that the bases overlap too. That makes it another detail. But, does that make sense?
Mm-hmm.
Okay.
Do you ever pick up from the overlap a cancelled out set?
Yes, but kind of rare. They don't overlap that much, but you could. There's a, I haven't done a lot of mitochondrial sequencing. I've done a little. There's one region is around 63, 65, I can't remember, that there tend to be 2 together. It's pretty common. Les could answer that.
150, 152?
Yeah, we'll never separate those 2, for instance. And I think those are both C to T, so that'll just happen. Yeah.
Tom, something you didn't mention very much about is the ability to catch deletions. Many of you do mitosequencing know there are various stretches where deletions are prone, like poly A stretches, that are specific to certain haplotypes. It's a no-brainer.
Yeah, actually, most of the time I won't even notice them if we're just doing a routine analysis. You'd have to compare them to something to realize you have it.
You work a lot with Hispanic populations.
The 290, 291
Yep,
deletions.
those are the ones I'm
Depending
thinking
on how
about.
your assay is set up, you may actually get primer failure and product failure. How your PCR primers are set up. So with this, the design of the primer and the degree of overlap between the adjacent products really
Confirms everything.
it confirms it, and also limits the amount of information that's lost if you're ever having polymorphism in the primer binding site.
We will see an occasional dropout, though. Outside of HV2 and rarely HV1, they're very rare, but there's a few scattered that aren't C-stretch where there could be a rare mutation on the 3' end of a primer. Say like 1 out of 30,000 dropped out. That can happen.